energy bands. Welcome to Decreations Resources. Let's consider a silicon atom. So atomic number is 14. So these 14 electrons will be distributed in 3 energy levels or shells from n is equal to 1 to n is equal to 3. And each shell can have 2n square energy levels. So they can occupy 2n square electrons. Now there will be 2 electrons in shell 1, 8 electrons in shell 2 and 4 electrons in shell 3. Now consider silicon crystal. The situation of a single silicon atom in isolation was different. Now in this case, when it is a crystal, each silicon atom will be surrounded by billions of atoms. So now the situation is going to change. Let us consider that there are n isolated atoms of silicon and each of these atoms have the electronic arrangement as described earlier for a single atom. So there are total n isolated atoms and they will have 4n valence electrons and 8n energy states in the outer subshell. Now when two atoms are brought close enough so that their outer subshell starts interacting with each other, then the similar energy level of two atoms will split because it has to satisfy Pauli's exclusion principle. So this, of course, we know that according to Pauli's exclusion principle, no two electrons can have the same quantum numbers. That means a single energy level cannot occupy more than 2 electrons. Now the split energy levels due to two atoms belong to both the atoms. That is, the electrons from both the atoms can occupy any of these split energy levels. So if you consider a system of two atoms, then you can add more atoms to that, and as more and more number of atoms will be added, the splitting of the energy levels will continue, of course all the time satisfying Pauli's exclusion principle. So in a crystal where many atoms are there together, the splitting of energy levels looks almost continuous. So it's as if it's a continuous set of energy levels, and this continuous set of energy levels is called energy band. So this is how for a silicon crystal you have energy band. So when you had a single atom, you had discrete energy levels, and when you have many atoms in a crystal, you have energy band with certain number of empty states and certain number of filled states. Now when atoms are brought closer, the attraction force increases due to the interaction between nucleus of one atom and electrons of the other atom. But if their interatomic distance is too small, then there will be a repulsion force as well due to the interactions between the two nuclei. So there has to be a balance between attraction and repulsion force, and this balance occurs at the interatomic distance equal to the lattice constant of each material. So the lattice constant, the distance we all the time speak about when you discuss a crystal system, that is basically the distance where the forces of attraction and repulsion are balancing. And this is a characteristic constant for each material. So for example, if you consider silicon, the lattice constant is 5.43 angstrom. In silicon, at interatomic distance corresponding to lattice constant, two energy bands exist and they are separated by a gap where no energy states are available. So this particular gap will be called energy gap, or the more well-known name is band gap, and the way we write it, capital E small g, Eg. So of the two energy bands, The upper energy band we call it as conduction band, and lower energy band we call it as valence band, and band gap is the distance between conduction band and valence band. And of course the reasons are clear. We call the lower band as valence band because valence electrons occupy this band, and the other band is called conduction band because conduction is when electrons basically go in upper energy band, only then conduction is possible. So now in a crystal of n atoms there will be 4n energy states in the conduction band and 4n states in the valence band. Now in a crystal of n atoms which has 4n valence electrons, out of the total 8n states, 4n can be occupied and 4n remain empty. So at 0 Kelvin, electrons will occupy the lowest energy levels available. That means at 0 Kelvin, all the 4n valence band states will be occupied by 4n electrons, while the conduction band will be completely empty.